Okay, probably I'll make a start while people settle in. So yeah, thanks again, Konstantinos, for the introduction. So in this part, I'm hoping to highlight some opportunities for integrating sensing and communications. Maybe start with, hopefully convincing you that it's a natural kind of integration. It was meant to be. And overview a little bit of the works in the area and some possible opportunities in this domain. So, to my observation, this research has all started from the growing scenario where where spectrum is being shared between radar and communication systems. So this involves the low gigahertz bands, where the classical conventional big radars live in, such as the long range surveillance, air traffic control radars, which have been already from 4G coexisting with LTE, and also now with 5G new radio, and also with wireless LAN as well. And this is going to grow even further, these coexistence scenarios, in the millimeter wave bands with these new types of radars, such as the automotive radar, the smaller, the more kind of down-to-earth radars, such as the automotive radars, the high-resolution imaging radars, which are scheduled to coexist with the newly released bands that are being released for 5G new radio. So these coexistence scenarios, many of them already, and this is going to be this is an increasing trend. And the coexistence looks something like this in a very basic format. So you have communication link, and at the same frequency, a radar trying to track or detect a target. And the key problem is the interference. So the interference that the communication transmitter causes to the radar reception of the echoes, of tracking, of estimating the target. And at the same time, the interference the radar creates to the communication receivers. And radars, especially the big classical radars, tend to emit a lot of power, right? And they can be quite disruptive. So to deal with this, so the classical coexistence strategies involve somehow managing this interference, somehow coordinating the two systems, synchronizing them, exchanging information, which tends to reduce, let's say, the efficiency of both links. And also, it's kind of a risky strategy for very critical applications. So radar critical applications such as air traffic control and so on, you cannot really tolerate any interference breach. And this has been, for example, a headline recently, earlier in the year, where planes were grounded of fears of 5G interference for their navigation systems and so on. But beyond the coexistence, there's a growing challenge of the increasing population of sensors and transmitters, and a classical scenario is the connected car. So the connected car will be expected to do a number of communication modes, together with a number of sensing modes. So vehicular communication will involve vehicle-to-vehicle links, vehicle-to-infrastructure links, vehicle-to-pedestrian links, and many others. And at the same time, the connected car will be equipped by a combination of sensors, including cameras, LiDAR, but also a range of different radars, so long range, medium range, and short range for all kinds of different sensing functionalities. From long range for cruise control or obstacle detection, medium range, again, cross-traffic alert, and again, obstacle detection, to short range, such as park assist, and many others. So a growing population of antennas, sensors, and so on for a combination of communication and sensing functionalities. We've also seen this problem raised in the military domain, where shipborne or airborne platforms typically carry a number of different equipment for these operations. So for communications and sensing, so friendly communications or enemy jamming, and also sensing such as detecting threats or mapping the environment, and many others. And each of these platforms, as we increase the requirements, the performance requirements, they tend to increase the antenna array size, the hardware, the power, and many other things. And this cannot go for long. I mean, you cannot keep increasing the hardware without end. So there's been a push for a long time in this domain to see whether these platforms can somehow be merged. Yet, for more than a century now, the two, let's say, technologies have been developed quite independently. And I put here this kind of ring fence over here, probably exaggerating a little bit, but it's true that they've been developed in silos. They've been borrowing ideas from each other, and we'll see some examples, but they've been quite isolated in terms of, we haven't had, let's say, technology that does both things. And there are some notable exceptions, with first one being from the radar domain, this pulse interval modulation back in the 60s, which we now consider as the first dual functional radar communication technology, where basically communication was embedded in a radar waveform, a good radar waveform, by modulating information on the pulse interval of the radar. Then around 2010 is when we started talking about the coexistence of radar and communications in terms of cognitive radio and all that, as a follow-up from communications with communications coexistence. And this, I guess, is probably the first time where we started thinking about these two systems together, at least coexisting. And since then, there's been a bit more of works. Again, maybe an example from the communication side. So, for example, using OFDM signaling for sensing, so as a reference signal to do my estimation for targets. But again, sparse for a while, until very recently. Yet, these two functionalities have a lot of commonalities in their functions. For example, one is beamforming. So we need beamforming for communications to make sure we constrain our signal energy in a direction and have a high gain link with minimal interference. We need beamforming for radar. When we want to push signal power towards a direction to illuminate a target, right? So this is a common functionality between the two. There's also commonalities in the theory and in the signal processing. We do hypothesis testing for communications. So demodulation is an example of a multiple hypothesis testing. So we're trying to determine which signal was transmitted. A very similar function is with target detection in space, for example, where we have these binary detection cells in angle and range. And we have either multiple binary hypothesis tests or multiple hypothesis tests over the different locations. There's also commonalities in estimation. So obviously we have channel estimation. We're trying to sense some parameters of the channel and determine some information from that channel so we can use for the transmission. And radar is basically an estimation process, right? We estimate parameters of the radar, parameters of the environment that tells us information about the target, sorry, not the radar. And there's also duplications in the hardware design. So multiple antennas. We have communications phased arrays for communications, phased arrays for radar. We've had for a long time multiple antennas for communications, so MIMO communications, and more recently MIMO radar. So a lot of duplication in the theory, in the signal processing, in the hardware design. So I hope this is convincing that, it was kind of meant to be, to have this sort of integration, which to our observation, it started probably a bit more systematically, maybe 5 years ago, in terms of coming up with technologies that with one transmission or one bit of hardware can do both things. And this integration is having this evolution path, which started from the coexistence, so the two separate signals interfering and us having to deal with it somehow to provide these two functionalities in a network, let's say. The co-located hardware concept, where we have, again, two separate systems, but either co-located or sharing the same hardware, where this coordination and this interference management becomes a bit easier. Then we have this joint signaling and processing, which is what I call the dual functional transmission. So with a single bit of hardware, a single signal, we do two things: convey information to the users, and also the same signal can be used to estimate a target or detect a target. And I guess the ultimate aim here, if we're talking about a 6G, so cellular networks, is having a cellular network. So if we imagine the 5G deployment already with these dense base stations all over the place, in walls of buildings, in lampposts over the street. Now these base stations, if you have this dual signaling, they're now not just communication base stations, but also sensors, right? So you have a very pervasive sensing through the cellular infrastructure. So the gains, there are a couple of obvious gains by integrating these two functionalities. So obviously the hardware gain, where before you had separate access point, let's say, and a radar transmitter, now you have this kind of super advanced dual functional access point. So a single device, doing both functionalities, estimating a target and conveying information. And that also has implications in power consumption. So it's one device consuming power, in complexity. So the hardware is reused, in energy efficiency, in savings of hardware and silicon, and so on. There's also the spectrum gain, which is something you gain already with the coexistence. So where before you had separate radar spectrum and communication spectrums that need to share with all kinds of other applications, now you have a bit of spectrum that's used by both, and you make more space for other applications to share the resources. A couple of non-obvious, however, gains are these scalable trade-offs. So now if you imagine you're co-designing the two systems, so you're co-designing from the start, the communication and the sensing functionality, you can design those such that you can achieve a scalable trade-off in the functionality you want to achieve. So from a full radar functionality to a full communications functionality by putting the priority on the communications, and anywhere in between. And we'll see some examples in terms of signal design. And finally, another benefit is the synergies between the two functionalities, where one can actually assist the performance of the other. So sensing assisting communications, for example, direction finding, assisting beam steering, and we'll see an example later on. But there are many other synergies that you can have between the two. And also synergies with other functionalities such as security, perhaps wireless power transfer that Yanis alluded to earlier, and many others. So a truly multifunctional device, a multifunctional network. And there's already a lot of buy-in from industry in these technologies. So major players such as Nokia, they're talking about joint sensing and communications. Here's an application in indoor sensing for health applications. Ericsson sensing is all over their 6G roadmap. Docomo and so on. Huawei has been preaching about this for the last 3-4 years, and they call it harmonized communication and sensing. So it's a key enabling technology for them as well. And there's also, about a year and a half ago, we've established an emerging technology initiative, an IEEE initiative, on this very topic, and there's a lot of interaction between industry and academia in this domain. So I'm going to focus on the signaling aspects of this technology. So in terms of the signaling, we have mainly 3 types of technologies of DFRC. By DFRC, I mean dual functional radar and communications. So first is what we call the radar-centric design, where the main principle is shown here. So you take a good radar waveform, a well-established radar waveform, and you modulate information on the radar waveform in some way, either on some parameters of the radar waveform, or through side lobe signaling, or through index modulation. And there's many techniques that fall under this category. And then you have a waveform that does 2 things at once, right? Both sensing and communications. There's a comms-centric design, so communication-centric design, where, again, the basic principle is you take a communication waveform and you use that as your reference signal for radar estimation. And then you have this transmission that is, again, dual functional, your usual communication business together with some estimation. Now, there's key advantages and disadvantages of these. So I would say the key advantages is doing DFRC through a comms-centric design means you do minimal changes in the communication transmission. So it's probably something that could be more easily implemented in the standards. And the same for radar. So you could take a radar system and modulate information on the radar system. But the truth is that the radar signaling is not designed for communications. The communication signaling is not designed for sensing. So there's limitations in the communication rates you can achieve with this kind of radar-centric design. There's limitations, and it's difficult to tune the estimation and the sensing performance of a communication waveform. And that's where the third category of technique comes in. So this jointly optimized design where you design the signal from the beginning. And you can design it as you want to achieve certain communications and sensing performances. And you can also design it such that you have this flexible trade-off between, as I said, full radar performance for radar critical applications, full communication performance for communication critical applications, and anywhere in between depending on your scenario. So with that kind of motivation and intro in mind, this is what I'm going to cover, a couple of areas, hopefully in the time we have. So first I'll show you some examples of weighted optimization based DFRC. So this joint design based dual functional radar and communications. Then I'd like to highlight something that I think is very important for DFRC, the security aspects of DFRC, and show you, hopefully convince you that these are kind of unique for these kind of systems. Then I'll talk about more of an application of this dual functional waveforms or signals in terms of these synergies that I spoke about, so in terms of sensing assisted communication transmission. And if we have time, we'll take a look at some recent experiments where we've done some experiments in our lab to convince ourselves that this can be done over the air. So first, in terms of weighted optimization, perhaps I won't go into too much depth in the math, but the scenario here is, as I said, we have this dual functional access point that wants to communicate to users, so transmit signals S to the users, the information signals, while at the same time with the same signal X is the signal we want to design, it wants to be able to estimate a target, either detect a target or estimate its parameters. So a classical communication model is this one, where H is the communication channel, and anything that lives inside H times X, aside of S, is interference. So we call that multi-user interference. So multi-user interference is measured by this metric. And then you can design a weighted optimization where you have the radar, so the communication metric and the radar metric. So here the communication metric is this multi-user interference. The radar metric is the proximity of the signal I'm designing to a well-known or an ideal radar waveform. So you design a radar waveform, X0, and then I'll design a dual functional signal that tries to approximate that waveform. And this is a weighted optimization in the sense that I have this weighting factor over here, which is between 0 and 1. And for low, so for high rho, so close to 1, this guy is the priority, this goes close to 0. For rho, close to 0, this guy goes away, and my priority is on the radar side, right? And you can see now how I can get this flexible trade-off between them. And you're designing a new signal X, and you can place all kinds of constraints on it. Here's an example of transmit power, which is important for cellular transmission. You can also have all kinds of other constraints, so per antenna transmit power, or constant modulus constraints if you're interested in hardware efficiency, or a few bit ADCs, which are common in the communications only literature, and so on. And a characteristic result that kind of highlights this trade-off. So by designing a new waveform that is flexible in terms of this functionality, you can actually trade off the radar performance. So here we have the example of omnidirectional signal for detection. So this is the radar probability of detection against the communications average rate. For a number of setups, I think we have 16 antennas at the base station and an increasing number of users. Sorry, the increasing number is this direction. The main message is that by tuning this factor rho, I can tune from a full radar performance to a full communication performance, so my maximum achievable rate, but also all the way in between by trading off between the two functionalities. It's also worth noting that even when I have my full radar performance, I have a non-zero, non-negligible communication rate. Even when I have my full communications priority, I have some sort of probability of detection. It's not just a random choice. And also this trade-off improves as I increase the degrees of freedom. So the ratio of antennas to users or targets. So it becomes more and more benign. So I can achieve my maximum rate with a minor sacrifice of the probability of detection, for example. And you can see many trade-offs of these, not just for detection, but for estimation and so on and so forth. So I hope it comes across that you have now a flexible trade-off between the two functionalities, which is something you cannot achieve with the comms-centric or the radar-centric design, at least not as easy as in this case. And we've tried this in our lab, just again to convince ourselves that this is not just theory. So here's a very elementary setup where we have a USRP array, 6 antennas, 2 communication users, and we're emulating a scenario where we want to transmit bits to these users while at the same time forming a beam, a steerable beam towards some direction. And we're measuring that beam using this directional antenna over here, using this weighted optimization that I showed earlier. So through this weighted optimization, as we tune the weighting factor, we're able to see the trade-offs over the air. So here we have the constellations of the signals received by the users together with the beam. So we're trying to form a beam towards some direction. And we can see we can achieve a beam of about 6 dB or so, PSLR, which is, I guess, what you can do with a 6-element array, but with a messy signal. And as we tune our priority towards the communication, so here's the perfect, let's say, communication scenario, very clear constellations, we lose this beam. But we have all these points in between where we can do both things with different priority. And with this system, we've been able to observe the bit error rates over the air for the communication users and also measure the quality of the beam in our lab. And more recently, we tried to take this a bit further to kind of close the loop in terms of the sensing functionality. So before we just showing that we can actually form a beam, now we tried to use that beam to do some very elementary activity detection. And the scenario we're emulating here is somebody, let's say, crossing the beam, so a people counter or detecting some sort of activity in the room. And we use this now as an obstacle to measure different power levels. So with basic power level detection, we've been able to provide some sort of elementary radar processing and sensing. We've been able, by tuning the threshold power that we use to determine whether or not there's an obstacle in the beam, we've been able to plot probability of detection and probability of false alarm and have a guard interval between them to make sure that there are viable thresholds that you can use to determine this activity. So very elementary over-the-air proof of this concept that with a single transmission, a single signal, you can do 2 things. But we can do better than that, better than just approximating a good radar waveform if you actually include a direct bottom line sensing metric. And here's an example of what you can do. So Kramer-Rao bound is a typical metric that measures the accuracy of estimation, basically, for radar. So here you can, instead of minimizing the distance of your signal to an ideal radar waveform, you optimize the radar metric directly. So minimize the Kramer-Rao bound, subject to SNR for the communication users, and transmit power constraints, right? A very basic optimization. And interestingly, you can see that you can still form a nice clean beam towards the direction you want. And also you get gains with respect to this radar approximation, waveform approximation design. So these 2 lines, so here we plot the bottom line metric, the CRB, so the estimation error basically, with the user SNR, with this threshold. And you can see the trade-off. As I increase the requirements for the users, I increase my estimation errors. These 2 lines represent what we get with this waveform approximation design. We're trying to approximate a radar waveform. And this is what you get when you optimize the direct bottom line metric. So about 3 to 4 dB in performance gain. So moving on to the second subject. So I'm hoping to highlight that, this dual functional radar communications has some key and unique security threats. So if you look at the scenario again, I have 1 transmission, 1 base station communicating to the users, and with the same signal, attempting to detect a target or estimate its parameters. Now, because my probing signal for the radar contains information, this means that this is now prone to target acting as an eavesdropper and eavesdropping this information that is meant to go to the users. And if the target is friendly, that's fine. But there's many scenarios where the target can be malicious or non-cooperative and so on. So it could be an enemy aircraft in a military scenario. It could be a malicious UAV in a civil kind of security scenario, or just a non-cooperative car that you don't want them to eavesdrop information about your link. And then this malicious target can either eavesdrop the information, and perhaps you can protect against that with some sort of encryption at the higher layer. But what you cannot protect is this target basically detecting that there's a link. And there are many scenarios where this can be critical information, important, especially military scenarios, where this can be important information for the enemy. So there's definitely need for physical layer security solutions. There's many of them in the communications only literature, so there's many that we can borrow to tune for this scenario. What's unique about this scenario? I think there's one thing that makes this unique and challenging and interesting. There's a conflict of objectives on the radar link, let's say. So on one hand side, you want to beam a lot of signal power towards the target. So you illuminate the target and you get a good return echo and a good radar SNR. But towards the same direction, if your target is now the eavesdropper, you want to limit the energy that the eavesdropper can get, the target can get to eavesdrop on your information. And at the same time, some classical constraints, you want to basically make sure that your communication users receive good quality signal, right? So conflicting objectives on the radar link, which are difficult to solve. And also another challenge is that if you have some sort of uncertainty in the location of the targets, you have to have a wider beam. That means you need to ensure security over a wider range of directions and angles. So how to solve this? So here's a couple of techniques. So as I said, on one hand side, you want to beam a lot of power to the target, and at the same direction, you want to limit the power of the useful signal that it can exploit to eavesdrop. So a very suitable technique is using artificial noise in your transmission. And here's, again, a bit too much math, but I'll go through it in a high-level description. So my transmit signal is now a sum of the pre-coded communication signal plus this artificial noise. And now the covariance of the signal, which is important for designing the radar beam pattern, is a summation of the two covariances. So this kind of achieves the fact that I can illuminate a lot of power towards this direction, but a lot of it, hopefully, is noise and is not useful from the radar as an eavesdropper. And with that, you want to design your precoder and the covariance of your signal. So the covariance, as I said, is used for the radar design. And here's an example design where we minimize the eavesdropping SNR of the target, making sure that there's not enough SNR for the target to eavesdrop the information, while at the same time forming a nice beam towards the direction of the target, a good peak to side lobe ratio. This is another typical radar metric, quality of the beam. And also we can tune the main region. So if we have an uncertainty over the location of the target, you can widen your beam or make it narrow according to what information you have. And this is done through these kind of constraints. At the same time, we have communication SNR, quality of service constraint, transmit power constraint, and a few other constraints relating to the formulation here. And this is solvable through classical techniques of convex optimization. Some key results. So first you see how the beam changes whenever I have uncertainty in the target location and increasing uncertainty of 10 and 20 degrees. You see for a fixed transmit power, you get a wider beam, but with a lower peak. And now the interesting part is this trade-off, again, another trade-off between the security performance and the radar beam pattern quality, the PSLR. A number of lines here, but the main message is, again, you can tune flexibly by tuning the parameters of your optimization between full security performance, full radar performance, and anywhere in between, right? As I increase the PSLR requirements, I tend to sacrifice some of the security. As I increase my security performance, I tend to sacrifice the quality of my beam. So again, another important trade-off between security now and sensing. And another technique that is also useful in this domain because of this conflicting objectives is the exploitation of constructive and destructive interference. And this is something that I've been working on for a number of years now, on the early days with EMAD during my PhD at some point, and more recently in my group in UCL. So this concept of constructive interference is looking at the modulation level of, or the constellation level of my signal. So any interference that pushes my signal away from the decision threshold, so if this is BPSK, the decision threshold is the 0 here. Anything that pushes me away is constructive. Anything that pushes me close, any interference that pushes me close to the decision threshold is destructive. And you can apply this to higher order PSK and other modulations, and we've done this over the year, and we'll see, we've seen that applying this can give you orders of magnitude reduction in the transmitted power for a given performance against classical beamforming or pre-coding techniques for communications only. And you can use the geometry of the problem to describe this mathematically. So if you take QPSK, for example, if you equalize all the phases here, all the constellation points fold onto the real axis, and your constructive region becomes this region. And with simple geometry, you can determine constraints for having your interference to the intended receiver constructive, right? And here's what you get with basic geometry. The interesting parameter here is gamma, which represents this distance. Distance is over here. So it's essentially an SNR parameter. So by tuning gamma, you have higher SNR or lower SNR. And you can use this kind of expression to replace classical SNR constraints. And now you can enforce constructive interference to your receivers. So how this applies to this scenario and why is it very suitable? Again, dealing with the conflicting objectives, you want to make sure that your legitimate users benefit from constructive interference, but your target as an eavesdropper falls in the destructive interference zone. In this way, you can, again, beam a lot of signal power towards the eavesdropper, the target, but it's not really useful for demodulating information when it wants to eavesdrop. And you can, again, design these kind of optimizations. So here's an example where we maximize the minimum radar SNR. So essentially, we maximize the radar performance, subject to constructive interference for these users and destructive interference for the target as an eavesdropper. And this is what you get. So these constellations over here. So we have one case where we only impose constructive interference to the users and do nothing about the target. And we have this case where we pose constructive interference to the users and destructive interference to the target. This is what we transmit, 1 plus J. This is what the users receive, so all in the constructive region, so they are able to extract the information. This is what the radar receives, so a random, let's say, signal, so it's a random choice. For the constructive case. For the destructive case, it's always outside the region of the useful signal. So it's kind of a secure, right? I hope it's obvious that it's a secure transmission. And we've measured the quality of the beam pattern, and we can form beams. And the interesting part here is the security performance, and we measure that with the symbol error rate over SNR. And the users achieve a good declining symbol error rate as I increase the SNR, while the target for the constructive only case basically does a random guess, right? So QPSK, we achieve a 0.75 symbol error rate. By destructive, by imposing destructive interference, you can push that closer to a symbol error rate of 1, so getting it wrong all the time. So let me move on to the next one. So as I said, an application of once you have this dual functional signal, what you can do in terms of synergies between sensing and communications. So I'll show an example through a vehicular communication scenario. So beam forming and beam steering in a vehicular scenario with communications only processes, it typically happens by the base station trying out a number of beams, the vehicular user, the communication receiver, estimating something about those beams, either the quality of the channel or the SNR it can achieve, or just the beam index that it prefers, and feed it back this information. And then if you want to further fine-tune the beam and make it narrower and a higher gain link, you need to iterate this process again and again, and you have dedicated resources in your frame, in your transmitted block, for beam training and feedback, right? And the rest, what remains is the space you have to transmit data. Now with DFRC signaling, you have now the scenario where you can actually transmit signal all the time and exploit the echoes, the radar echoes, and the radar direction finding to inform where your next beam needs to point and establish a good narrow beam high gain link. And in this sense, because your signal is now dual functional, you can use the entire block for this for both functionalities. That means you don't need to dedicate resources just for channel estimation or beam tracking. You also you're not let's say subjected to feedback errors, either quantization errors that this guy needs to quantize information and transmit, or errors in the feedback link. The whole frame can be used for sensing, which means you have a better integration and match filtering gain for your sensing, so better sensing performance. And this we'll see that gives you significant gains in terms of establishing and maintaining a link in high-speed scenarios. And this is an example of how you can apply this. So here's a scenario where you have a base station and a vehicle moving in a straight line across the base station, and through geometry you can basically express this as a state transition model where the state is evolving, and the model here can involve all the radar parameters such as angle, which is useful for the beam steering, but also distance, velocity, radar cross-section and path loss, and so on. And you can use the radar measurement model and some from simple match filtering or more advanced techniques to obtain estimates of your round trip delay, so your distance, your Doppler offset, so your velocity, but also information of theta. Theta is now the angle, which is useful for the beam steering and beam prediction. And you can use that angle to predict the next angle and the velocity information and steer your beam proactively so that you can follow the vehicular user. So you can see that through this dual functional signaling, you save the effort of the feedback and the resources of the feedback and all this errors that is prone to. Again, an illustrative result. So here we plot the achievable rate with time, and as time passes, we have this vehicular user crossing the area of a base station, so getting closer and then far away. And you can see, so we compare three techniques, two communications only techniques. So one is a beam training scheme, which is based on the feedback that I mentioned and extended Kalman filtering to predict the next beam. The second one is the beam pair approach, so where basically the user selects between a pair of beams, which one it prefers. And the third one is the DFRC approach, this dual functional signaling, again with basic Kalman filtering for prediction. And what you can see is all techniques, they establish a link, let's say, and they can maintain a link with a good rate. But at some point, at this point over here, as the vehicle comes closer, the angle change becomes faster and faster, right? So the beam pair technique cannot keep up with that, because possibly the optimal beam is outside the pair because it's changed so fast. So you lose the link here, right? So there's a failure, there's an outage here in the link. The communications only technique maintains the link, but it suffers again from the channel estimation performance, because again, the directions change so fast, you're not able to keep up with tracking the channel. The DFRC technique is able to maintain a good link and also increase the rate as the path loss reduces, right? I keep a good established link, a good high gain beam that keeps increasing my rate. So you can see by using the entire block, I get better sensing performance, estimation performance, direction finding performance, and also I maintain a good communication link. And the final thing I'd like to talk about, we're good with time, I hope, is another experimental study on this radar-centric DFRC. So the one I spoke about, where you use a radar waveform to convey information. So we've used the technique of index modulation, DFRC with index modulation. Probably the best place to read about this is this paper a couple of years ago, where the authors basically use a MIMO radar, a classical MIMO radar transmission, and they encode information on the antenna used to convey the signal, so spatial modulation, for those of you who are familiar, and also on the frequency index that is used. So a combination of antennas and frequency index gives you a constellation And through that constellation, you convey the communication information. So the example here, 2 antennas, 4 frequencies, give you 8 possible combinations. So 8 combinations will describe 3 bits in the transmission. And you can calculate the spectral efficiencies and so on. You can find all the details in this work. So we've applied the same principle in this is now our radar lab in UCL. So where we have the radar transmit antenna and receive antenna, an emulated target, and a communication receiver. It obviously is not a MIMO link. So what we can tune here is not the antenna index. It's so we have this RF system on chip platform that can produce different waveforms. It's flexible in terms of the radar waveforms it achieves. So we have a linear frequency modulated waveform that we can tune its center frequency, its bandwidth, and the polarization that we use for the transmission. And through this combination of these 3 elements, we can build a large constellation. So we use this combination of things, and if you do the math here, we can achieve 10 bits per symbol that we transmit. Each symbol is transmitted per radar pulse. So the key parameter we tune is the pulse duration. And the pulse duration, we tune it between 1 and 100 milliseconds. So narrow pulse duration will be good for communications. It means you can transmit more pulses per second, so more of these 10 bits per second, right? But a narrower pulse means the radar integration gain is diminished, right? So radar wants a wide pulse, communication wants a squeezed pulse, so they can convey more of those per second. So by tuning this parameter, you again can establish a trade-off between sensing and communications. So here's the communications only performance, throughput with SNR. And this is how it increases when you reduce the pulse duration, so more of these symbols per second. And here are also some direct trade-offs between radar performance and communication. So the radar SNR we achieve once we receive our echo and do our match filtering and integration against this maximum throughput. So these plateaus here that we can achieve for different TP over here, pulse durations. And you can see as I increase my pulse duration, as I reduce my pulse duration, I increase my throughput at the expense of my radar SNR. As I increase my pulse duration, I go the other way around. And also we've extrapolated the estimation errors, the CLRB. So again, the throughput against the range estimation performance of this transmission. So again, another flexible trade-off that we've been able to design through radar-centric design. So that's more or less what I had to say in terms of ongoing work. A bit of a vision or an outlook of how I see this going. So I think there's a lot of work still for us to do in terms of waveform and signaling design, making this more hardware efficient, making it hardware informed, and reducing complexity as well. Most of the stuff you've seen is based on optimization. So it's a key question, how can you do this in closed form or in suboptimal ways? There's plenty more in terms of synergies. Sensing-assisted communication is just one of these synergies. Even in there, you have lots of more complicated problems. What happens if you have multiple vehicles? How can you track all of them and beam steer for all of them? What happens if you have complicated trajectories, not just a straight line? What happens when you treat the vehicular user as not as a point target, but actually a vehicle with a shape and geometry? How can you tackle that? There's also plenty to do in this domain that I hope I convince you that it's important in terms of security, in terms of securing against eavesdroppers, and also that represents another synergy where the direction finding of sensing can assist in identifying potential eavesdroppers, right? And null steering against those directions. And I guess the ultimate goal, as I presented earlier, is to have this cellular system that is doing two things. It's also a sensor along with communication infrastructure. And to get there, there's also a lot to do in terms of multi-cell DFRC and also multi-static, so bridging the gap between multi-cell communications and multi-static radar. There's also plenty of stuff to do in terms of energy autonomy, and that's something that closely relates to PAINLESS. There's plenty open problems, for example, in making these dual functional access points powered by renewable sources or hybrid sources. There's plenty of scope in applying these kind of principles in drone-based or aerial communication systems. Also navigation and swarm control of drones, where you need both navigations of sensing and communications between different drones to address all these kinds of scenarios, very relevant scenarios. So I think I'll end here, and I'd like to thank all the people that have worked in these areas. Two of them, Iman and Xiaoye, are here, so feel free to hunt them down and ask them questions, and also acknowledge the funding that has made this possible. And with that, I'll end here, and I'm happy to take any questions.
Okay, any questions in the room? Do we have any questions remotely? Do we know? Okay, if not, and since we're also running out of time, thank you very much, Chris. Excellent overview and great topic too.